All right, so we're making our way through question 3 here. Question 3, originally A and B were together as one question, but, we kind of separated things out here again, and that's fine. I kind of changed it up a little bit. So again, I would point you guys to the 5 W's, the who, what, when, where, and why. Right? Now, you notice we don't have our buddy benzene here, so that's something important to recognize. So something to discuss would be, definitely mention that this is still an aromatic compound, and we are still doing an electrophilic aromatic substitution, right? We're adding bromine, but again, no catalyst. So what would that tell you about this aromatic system? Well, it'd be highly activated, right? So that'd be just like what we kind of talked about here with this question, right? We don't need a catalyst for it to be able to attack that bromine. That's interesting. We have a major and a minor product, right? We have the positions next to the sulfur there. Those would be identical, right? And then we'd have the 2 positions here. So we really only have 2 spots where the bromine could be added. Remember, and this was a confusion, and there are no ortho, meta, and para are only on benzene rings. Okay, so anywhere else you describe it with numbers or something like that, right? So just be careful of that. I didn't necessarily count off for that. Just be careful, right? Be very deliberate with how you're describing things. So definitely there should be some discussion about that this is an aromatic system, that it is activated, that we have a major and a minor product. That'd be useful, and you have to draw the mechanism for this. You have to. This is what this question was asking, saying, hey, do you understand why the major and the minor product happen here? And you guys are like, and a lot of people said, well, because there's more resonance. Draw it for me. Like, okay, you guys, I don't know what it is. You guys were like, were trying to hold back from me the information that I know you guys knew. Put it on paper, right? Put it on paper. Don't just tell me there's resonance structures. Draw them, right? So if we real quickly go through and, we start out this mechanism here. We make a bond, we break a bond. There's this, so let's put the bromine there. So now we've got a positive charge here, right? So resonance structure number 1. That looks nice. And then resonance structure number 2, right? Not as nice, but still not bad, right? If we go the different route there, where we add it to the 3 position, then we can only draw that one resonance structure there, and that is a good explanation for what we end up seeing, right? We end up seeing 2 resonance structures as opposed to, just one resonance structure, or 3 if you want to say that. That'd be fine too. 3 versus 2, right? That would probably be a better argument to make in this case. 3 versus the 2 here. And that would help explain why we see the addition at the 2 position there, right next to the sulfur, right? Resonance structure. So draw them out, right? Very clear explanation. Then all you have to do is say, we have these resonance structures here. There's more resonance structures with this addition. That's why the higher yield. We talk about the ring being activated because we don't have a catalyst around, and that's good, right? We don't have any kinetic information here, right? So we can't really make too many arguments about when and all that kind of stuff, but there we go. Okay. Now, B, right, should be answered in very much the same way, okay? B should be answered in very much the same way, because what I was trying to get you guys to do here is take a look and say, well, right, we've got 3 potential positions where we could add that bromine. This up here gave us, a huge hint about, where it should be added, but why wouldn't it be added at the green or the red? And the answer for that is, well, go through and draw the mechanism, right? The reason why it wouldn't be added here would be sterics. And the reason why it wouldn't be added here is electronics. Okay. The green and the purple positions are both the preferred positions due to resonance. Well, I guess you could even say electronics here too, right? The reason why you wouldn't add it at the green position is sterics and electronics. The reason why you wouldn't add it at the red is electronics, right? It would put a positive charge next to a deactivator here, right? So just because we don't have a benzene ring doesn't mean that this isn't a deactivator, right? Deactivators are deactivators, and there's, a million billion examples of aromatic rings, and, they all behave the same way, right? That's why understanding the concepts behind all these is what's going to be important. So definitely draw a mechanism for this one here, and show the stability of the carbocation, right? Why wouldn't it go to the red? Why would it prefer the purple? That kind of stuff. Okay. This last reaction here is kind of the same, and some of you guys did a lot of work to go kind of dig down the actual mechanism for this, and that's fantastic, right? So a couple things to note here, a little bit more complex. If you guys went through and drew the mechanism for the formation of the cation, that's awesome, right? We notice we have some different aromatic rings, right? We've got a benzene ring fused with another ring up here, whereas we just have a benzene ring. We notice that the aldehyde is not added to the benzene ring. Now that should be important, right? That's a big where to be answered, right? It's a big where to be answered. So to kind of help answer that where, what we can do is take a look at, again, resonance structures, right? So if I think about this, right? If I draw what happens with that lone pair there, just for argument's sake, right? You see I can push a negative charge onto this, right, onto that carbon there, right? Well, why is that important? Well, that's exactly where our aldehyde gets added, right? So we have some negative density that's at that position there. So what does this tell us? This tells us that this part of the ring is also the activated part of the ring. Okay. We can resonance stabilize this with that lone pair from the nitrogen. We know we have a negative electron density at that carbon. So that helps us to explain why this is going to be faster, right? And why it has a better yield here also. Okay. But again, it comes down to drawing the resonance. I didn't expect you guys to do the mechanism for this one, right? I don't think this one's in the book. But if you guys did it, that's great also, right? That's great also. So what else does this tell us? It tells us that this needs, right? It needs an activated ring for this to work, right? 30 minutes versus 72 hours, right? So we need to have negative on the ring itself, right? So there would be an argument for you guys to say here about we have an activated ring or a deactivated ring. You could make some kind of argument about aromatic and retaining aromaticity versus a homoaromatic system, right? Versus a heteroaromatic system, these kind of things, right? That'd be just fine also. But really the point comes down to, drawing through some things, talking about it, looking at the data, discussing it in that way, okay? So I think, like I said, I don't want to make a bunch of 40-minute videos kind of saying the same thing. Hopefully you guys get the idea about, when I'm asking you these types of questions, and I will, draw out your mechanism, right? Take a look at it. That's what's going to help us explain it, right? Take a look at sterics, take a look at electronics, take a look at the who, the when, the where, and the why, all that kind of stuff that kind of comes together in this, okay? All right, I think we got one more video to go next time about the last page, and then that'll be it for this exam. All right, see you guys in the next video.